Introducing the Mise en Place Culture First podcast, where operational excellence begins and ends with you. Let's get started.
You know, it's usually when you walk up to a restaurant and you see that bright blue A grade from the health department sitting there in the window.
Right.
There's this built-in expectation of simple cleanliness. You know, you imagine a guy with a mop, some bleach, maybe a manager who just makes sure the floors aren't sticky.
Yeah, totally.
And that's kind of it.
It feels very binary, I think, to most people on the outside. Like a kitchen is either clean or it is dirty. You wipe down the counters, you wash the dishes, you get an A.
Right, right. It's comforting to think about it that way. We like things to be visible and, easily categorized. But I've been reading through this massive stack of sources for our deep dive today. We've got the 2022 FDA Food Code, this whole pile of state health department guidelines, commercial equipment specs, and some really dense industry compliance manuals regarding federal regulations.
Oh, yeah, it is a lot of reading.
It is. And suddenly, that mop and bucket don't even scratch the surface. The level of microscopic warfare happening in a restaurant kitchen is staggering. It is this highly structured, intensely rigid scientific process.
It really is a high-stakes battleground. The sheer volume of variables that have to be controlled perfectly every single day, just to serve a simple cheeseburger safely, it requires an incredible operational system.
Yeah.
And what's interesting is that while your local health inspector is the one actually walking through the front door with a clipboard, they are almost all operating from a single foundational blueprint, which is the FDA Model Food Code.
Right. And I noticed the 2022 edition we're looking at, it actually commemorates 30 years of the food code in its current format.
Mm-hmm.
But the sources keep calling it a model code. If it is FDA airs as absolute best scientific advice for, keeping people from getting sick, why is it just a model? Doesn't the federal government just mandate this for everyone?
You would think so, yeah, but food service regulation in the United States is it's highly decentralized.
Yeah.
The federal government doesn't directly inspect your local neighborhood diner. That falls to the state or county or, city health departments.
Mm-hmm.
So the FDA creates this incredibly comprehensive, scientifically backed document, the Model Food Code.
Mm.
And they essentially hand it to the states and say, here is the gold standard. We strongly suggest you adopt this into your local laws.
And most of them do, right?
Overwhelmingly, yes.
Yeah.
Some states might tweak a minor detail here or there, maybe adjust a temperature requirement by a degree, but it serves as the regulatory North Star for over 1 million facilities nationwide.
Wow.
We're talking white tablecloth fine dining, food trucks, grocery store deli counters, school cafeterias, even nursing homes. They all fall under the shadow of this one massive rule book.
Okay, well, let's unpack this rule book then, because reading through the inspection guidelines, the scoring system is intense. If we want to understand how a kitchen actually keeps food safe, I feel like we first need to understand how they are graded and, what happens when they fail. So most state and county health inspectors use a 100-point inspection model, right? That's the standard.
To the standard baseline, yeah.
Yeah.
You start with 100 points, which is a perfect score, and the inspector deducts points for every infraction they find. But the crucial thing to understand is that the FDA categorizes violations into 3 distinct tiers based on the actual biological risk they pose to the public.
Okay.
You have priority, priority foundation, and core violations.
I want to look at the massive red flags first, the priority items.
So priority items, which older versions of the code actually called critical violations, are the absolute deal breakers.
Right.
These are mandatory provisions directly linked to eliminating or reducing hazards that cause foodborne illness. If a kitchen fails here, someone is likely going to get sick.
Like what?
We are talking about raw chicken juices visibly dripping onto ready-to-eat salad greens in the refrigerator, or a cook handling a fully cooked burger bun with their bare, unwashed hands.
Oh, man. And a single priority violation usually results in a massive 4 to 10-point deduction, depending on the state, right? And from what the compliance manuals say, it requires immediate on-site correction.
Immediate. Yeah, the inspector will literally stand there and watch the manager throw the contaminated food into the trash.
Okay.
You don't get to fix it tomorrow. It's done right then and there.
Okay, so then the next tier down is priority foundation, which sounds similar, but the sources frame it more as the infrastructure behind the rules.
Think of it as the systems that support the priority items. So priority rule is you must wash your hands.
Okay.
But a priority foundation rule is there must be soap and paper towels at the designated hand-washing sink.
Right, because if you don't have soap, you can't follow the priority rule.
Exactly. Or if a kitchen doesn't have, like, calibrated food thermometers available for the cooks to check the internal temperature of a chicken breast. Those are priority foundation violations. They haven't necessarily poisoned anyone yet, but the safety net is gone. Those typically carry a 2 to 5 point deduction.
And finally, the core items. Now, this tier seems to cover what a normal customer might actually notice if they peeked into the back.
Yeah, core items focus on general sanitation, facility maintenance, and what they call good retail practices.
So like a dirty floor.
Right, a floor that hasn't been swept, or maybe an uncovered plastic container of flour in dry storage, peeling paint on a wall in the dish pit, or a dusty ventilation hood. These usually only cost 1 to 2 points. They matter for overall cleanliness, but a dusty vent hood isn't going to cause an outbreak of E. coli by itself, you know?
Right, okay, but wait, let me run a scenario by you. Let's say I'm running a restaurant.
Okay.
My kitchen is gleaming, the stainless steel is polished, the floors are spotless, the vent hoods are pristine, but one of my line cooks is rushing, completely forgets to wash their hands after handling raw fish, and the inspector catches it. That's a priority violation. Can I fail the entire inspection just for that one mistake? I mean, is it like a driving test? You know, you can parallel park perfectly, check your mirrors flawlessly, use your turn signals, but if you roll through one single stop sign, the instructor fails you instantly, regardless of how good the rest of the drive was.
It is very much like a driving test in that regard. You can absolutely fail an inspection for a single severe priority violation.
Really? Just one?
Just one. If an inspector walks in and finds a pest infestation, or raw sewage backing up from a floor drain, or a walk-in cooler that is completely failed and is sitting at 60 degrees, they won't just deduct points. They possess the legal authority to shut the establishment down on the spot until that imminent health hazard is corrected.
Oh, wow. But looking at the commentary from the industry experts in our sources, a catastrophic failure like that, or an actual foodborne illness outbreak, it rarely comes from just one isolated mistake.
It almost never does. Contamination in a commercial kitchen operates on the concept of accumulation. It's the Swiss cheese model of failure.
Okay, the Swiss cheese model. I've heard this used in aviation, but how does it apply to kitchens?
Yeah, so imagine several slices of Swiss cheese stacked together. The holes in the cheese represent vulnerabilities, shortcuts, or just small mistakes. In a normal operation, a mistake on the prep line is caught by an observant manager, or a bad ingredient is caught by the chef during receiving.
Right, so the holes don't line up.
Exactly. The holes of the cheese don't line up, so the hazard is blocked by the next slice.
But the kitchen environment is incredibly chaotic.
Extremely chaotic. Picture a Friday night dinner rush. Tickets are printing out of the machine nonstop, staff are in the weeds, maybe 2 dishwashers called in sick.
Yeah.
In that stress, a cook skips a 20-second hand wash to save time. That's one hole. A manager is too busy expediting food to check the concentration of a sanitizer bucket. That's a second hole.
Oh, I see where this is going.
A piece of raw chicken slightly brushes against a cutting board that later gets used to chop parsley. Yeah. A third hole. When all those holes align perfectly, the hazard slips all the way through the system and a contaminated plate of food reaches the dining room.
It's this cascade of small shortcuts.
Yeah, exactly.
And if we step out of the inspector's rulebook and into the physical space of the kitchen, all the sources point to one specific room as the ultimate battleground where these cascades usually begin. And that's the walk-in cooler.
Oh, the walk-in cooler. It is the beating heart of any restaurant, but it is also where basic gravity becomes a facility's biggest liability.
Gravity.
Yeah, but before we even talk about how things are placed on the shelves, we have to talk about ambient temperature and something called the danger zone.
Right, the danger zone.
Yeah.
This is heavily emphasized in the FDA food code regarding TCS foods, which stands for Time Temperature Control for Safety Foods. This is basically anything bacteria loves to grow on, right?
Yeah.
Raw meat, dairy, cooked rice, cut melons, baked potatoes.
Yep, all of that. The danger zone is the specific temperature range between 41 degrees Fahrenheit and 135 degrees Fahrenheit.
Okay.
Within that window, bacteria don't just survive, they thrive and multiply at terrifying rates. Under ideal conditions, certain bacteria can double in population every 20 minutes.
Wow. And the food code places a strict, non-negotiable time limit on how long a TCS food can sit in that zone, right? 4-hour rule?
Yes. If a TCS food sits in the danger zone for a cumulative total of 4 hours, it crosses a biological point of no return. You cannot save it. You can just throw it back in the walk-in to cool it down, and you can't just throw it in a fryer or an oven and cook it to death to make it safe.
Wait, why not? Because if I take a piece of meat that's been sitting out all day and blast it in a 500-degree oven, won't that kill the bacteria? I mean, heat kills bugs.
Fuel kill the bacteria, yes. But the bacteria aren't the only problem anymore.
What do you mean?
While they were multiplying in the danger zone for those 4 hours, those bacteria were actively producing toxins as a byproduct. Heat kills the living organism, but it does absolutely nothing to the toxins they left behind. The toxins are heat stable.
Oh, wow. I never thought of that.
Yeah, if someone eats that meat, they are still going to get violently ill from the toxins. So at the 4-hour mark, it must be thrown in the trash. No exceptions.
Okay, but I have to push back here. A cumulative total of 4 hours.
Yeah.
If I'm health inspector, right, and I walk into a kitchen at 2:00 p.m. on a Tuesday, and I see a massive tub of cut cantaloupe sitting on a prep table at room temperature, how do I possibly know if it's been there for 30 minutes or 3.5 hours? I mean, I can't look at a melon and read its history.
Which is exactly why the burden of proof is entirely on the restaurant.
Okay.
This is where meticulous logging and date marking come into play. If a kitchen is pulling a TCS food out of the fridge to prep it, they must have a visible timestamp on that container or a working log nearby proving exactly what time it left the 41-degree environment.
So they have to write it down every single time?
Every time. If an inspector points to that tub of cantaloupe and the manager cannot instantly produce a time log showing when it was pulled, the inspector will just assume it has violated the 4-hour rule and force them to throw the entire batch away on the spot.
Wow, so the documentation is just as important as the temperature itself?
Absolutely.
All right, so assuming the walk-in cooler is doing its job and holding a perfect 38 degrees, the food is safe from the danger zone. But that brings us to the physical layout of the shelves inside that cooler, and the FDA is incredibly strict about this. You can't just play Tetris and put things wherever they happen to fit. There is a rigid top-to-bottom vertical hierarchy.
A hierarchy based entirely on one single scientific metric, which is the minimum internal cooking temperature of the specific food item.
I was looking at the diagram for this in the sources, and the logic is fascinating. Walk us through a standard shelving unit in a commercial walk-in cooler, from the ceiling down to the floor.
Okay, so on the very top shelf, closest to the ceiling, you are only permitted to store ready-to-eat foods, RTE.
Okay, meaning no cooking required.
Right. These are items that require absolutely no further cooking before they are placed in front of the customer. Pre-washed salad greens, cut fruit, baked desserts, prepared sauces, blocks of cheese.
Got it.
Then, moving down to the second shelf, you have whole fish and seafood. The FDA minimum internal cooking temperature to neutralize pathogens in seafood is 145 degrees Fahrenheit.
Okay.
On the third shelf, you store whole cuts of intact meat. So raw beef steaks, pork chops, lamb. These also require a 135-degree minimum cooking temperature.
I'm assuming fish and whole beef can occasionally share a shelf if space is tight, since they both cook to 145.
They can, technically, though. Best practice keeps them separated to prevent flavor transfer. You don't really want your steaks tasting like salmon.
Fair enough.
But the crucial shift happens as we move lower. On the fourth shelf down, you find ground meats. Ground beef for burgers, ground pork, bulk sausage.
Because ground meat requires a higher cooking temperature, which is 155 degrees Fahrenheit. But why? This is the thing I kept wondering. Why does a solid piece of beef cook to 145, but if I grind that exact same piece of beef up, suddenly it needs to be cooked to 10 degrees hotter?
It's all about surface area.
Surface area.
Yeah. When you have a whole, intact cut of steak, the dangerous bacteria is almost entirely residing on the outside surface of the meat. The interior muscle is essentially sterile.
Right, because the bacteria hasn't penetrated the muscle fibers.
Exactly. When you sear that steak in a pan, the outside hits a massive temperature very quickly, killing the pathogens, even if the inside remains rare or medium rare.
Okay.
But when you run that meat through a grinder, you take whatever bacteria was on the outside surface and you mix it thoroughly throughout the entire inside of the patty.
Oh, gross.
Yeah, the bacteria is now everywhere.
Oh.
So you have to bring the entire internal mass of the burger up to 155 degrees to ensure it's safe.
That makes perfect sense. Okay, so ground meats are on the fourth shelf, which leaves the bottom.
On the absolute bottom shelf, resting just above the floor, you have raw poultry, chicken, turkey, duck. This is the highest risk item in the entire kitchen. It is known to heavily carry Salmonella and Campylobacter, and it requires the highest minimum internal cooking temperature of 165 degrees Fahrenheit.
It's basically treating gravity as a hazard.
Exactly.
As I was reading the manual, it struck me that it is like a reverse high-rise apartment building.
Oh, I like that.
Yeah, you force the most dangerous, unruly tenants to live in the basement. That way, if their plumbing breaks and they cause a leak, they can't drip through the ceiling and ruin the apartments below them. There's nothing below them but dirt.
That is the exact mechanism the FDA is relying on. Because think about it, if a container of raw chicken juice leaks from the top shelf onto a box of lettuce, that lettuce is going to be served raw. The bacteria survives, the customer eats it, and they end up in the hospital. But if raw chicken juice drips from the bottom shelf, it just hits the floor. It's a mess, obviously, but it's not a biological disaster. And let's look at the middle shelves. If raw steak juices accidentally drip down onto a batch of ground beef below it, it's a violation, but practically speaking, that ground beef is going to be cooked to 155 degrees anyway.
And that is hot enough to neutralize whatever pathogens drip down from the 145-degree steak.
Exactly. The physical layout of the room is a fail-safe against human error.
And speaking of the floor, there's another physical rule in the walk-in, and really everywhere in the facility, which is the 6-inch rule.
Right. Absolutely nothing can be stored directly on the floor. Every box of onions, every bucket of marinade, every bag of flour in dry storage must be elevated at least 6 inches off the ground.
Is that just so the dishwashers can get a mop under there at the end of the night?
Mopping and facility cleanliness are a big part of it, for sure. But the primary driver behind the 6-inch rule is actually pest control.
Oh,
A health inspector needs clear visual access. They need to be able to shine a flashlight along the floor-wall junction of the entire room to look for rodent droppings, insect casings, or nesting materials. If a kitchen stacks cardboard boxes directly on the floor, they're creating dark, warm, undisturbed harborages for pests and completely obscuring the inspector's view.
okay, so the food is stored perfectly, the delivery was time-stamped, the chicken is in the basement, everything is 6 inches in the air.
Right.
But then a cook opens the door. And the moment a human touches the food, the systemic safety nets basically fall away and the risk resets completely.
It really does.
Let's look at the tools and the habits used during actual prep. The sources spend a lot of time on hand washing, specifically something called the double wash technique.
The double wash technique is mandatory after high-risk activities, primarily after using the restroom or handling raw proteins. If an employee uses the restroom, they wash their hands at the sink inside the restroom.
As you should.
As you should, obviously. But when they re-enter the kitchen, before they touch a single piece of equipment, a cutting board or a knife, they must immediately walk to the designated kitchen hand sink and wash their hands a second time, vigorously, for 20 seconds.
And it has to be a designated hand sink. I noticed the code is very particular about sink usage. You can't just wash your hands in the massive 3-compartment sink where they wash the pots, or the prep sink where they rinse the lettuce.
Never. Sinks are strictly segregated by purpose. Using a food prep sink to wash your hands is a massive priority violation because you are splashing whatever bacteria was on your hands all over the space where fresh produce is prepared.
Right, that defeats the whole purpose.
And the FDA also enforces a zero-tolerance policy for bare hand contact with ready-to-eat foods. If a cook is plating a cooked burger, building a salad, or garnishing a cocktail, their bare skin cannot touch that food. They must use tongs, deli tissue, or gloves.
Well, gloves. You know, as a customer, you look into an open kitchen, you see a line of cooks wearing black nitrile gloves, and you instantly feel a sense of safety.
Yeah, everybody does.
But the compliance manuals are very clear that gloves can actually be one of the biggest liabilities in the kitchen. They offer this total false sense of security.
People treat gloves like a magic force field. They are not. They are just a single-use barrier. The psychology of gloves is actually a huge problem in food safety, because an employee wearing gloves stops feeling the grease, the moisture, and the food residue on their hands.
They stop feeling dirty, so they don't think to wash.
Exactly. The glove protects the cook's hand, not the customer's food.
Right.
If a cook puts on a pair of latex gloves, picks up a raw chicken breast, throws it on the grill, and then uses those exact same gloved hands to grab a handful of fresh spinach for his salad, the cross-contamination still happened.
Yeah.
A glove can carry salmonella just as easily as bare skin. The rule is that gloves must be changed every single time an employee switches tasks. And crucially, they must wash their bare hands with soap and water between every single glove change.
That requires an exhausting amount of discipline during a busy shift.
It really does.
It is no wonder they say cross-contamination is a cascade of small shortcuts. To help bypass that human error, kitchens rely on visual systems, the color-coded boundaries.
This is a brilliant operational strategy to take the decision-making process out of a stressed line to cook's hands. Kitchens use distinct color-coded cutting boards, knives, and tongs for different categories of food.
So what are the colors?
So red is universally for raw meat. Yellow is for raw poultry. Blue is for raw seafood. Green is for produce. And white is for dairy or bakery items.
So if a manager is standing at the pass looking across a busy kitchen and they see someone chopping tomatoes on a red cutting board, they instantly know a severe cross-contamination hazard is occurring.
Right, they don't even have to walk over and ask what was on the board previously. It's a visual alarm system.
It creates a physical and visual boundary that drastically reduces the cognitive load on the staff.
Exactly.
Here's where it gets really interesting, though. There is another color in that system that the manuals highlight: purple. And this deals with a completely different kind of threat: food allergies.
Yes. The purple cutting boards, knives, and pans are exclusively reserved for allergen-free orders. And this highlights one of the most vital distinctions in all of food safety, which is the difference between cross-contamination and cross-contact.
I always thought those terms were interchangeable. I mean, they sound like the same thing.
They sound similar, but biologically and procedurally, they're entirely different threats. Cross-contamination deals with living organisms, bacteria, viruses, pathogens like E. coli. If bacteria gets onto a piece of food or a stainless steel table, you can often neutralize it.
Okay.
You can cook the food to a high temperature to kill it, or you can wipe down the table with a chemical sanitizer to destroy it.
But an allergen isn't a living organism.
No, an allergen is a protein.
No.
A peanut protein, a shellfish protein, gluten. You cannot kill a protein.
Oh.
If you put a peanut in an oven and heat it to 500 degrees, it's still a peanut. And if a customer with a severe allergy eats it, it will still trigger a life-threatening anaphylactic reaction.
Oh, yeah.
Furthermore, chemical sanitizers do not destroy allergen proteins. You cannot just wipe down a cutting board with bleach and assume that trace amounts of walnut are gone.
So cross-contact is when an allergen protein is transferred from one food or surface to another. And because you can't just sanitize it away, it requires a completely different workflow.
Right. When a severe allergy order comes into a commercial kitchen, the standard rules aren't enough. They have to pull the purple equipment. Often they have to prepare that dish in a completely separate, dedicated buffer zone in the kitchen to ensure zero trace transfer from a cutting board, a stray crumb, or even a shared fryer vat.
That's intense.
This is about total isolation, not just sanitation.
Well, since you can't just wipe an allergen away, it forces us to look at the chemistry of how these kitchens actually stay clean. This is another area where I think the average person at home probably has the wrong idea. There is a massive regulatory difference between cleaning a surface and sanitizing a surface.
It is perhaps the most fundamental concept in the FDA Food Code. There are two entirely separate sequential steps.
Okay, walk me through it.
So cleaning is the physical removal of visible debris, grease, soil, and food residue. You use soap, water, and mechanical friction to achieve a surface that is clean to the sight and touch.
Like washing dishes.
Right. But sanitizing is the physical or chemical process of killing the microscopic pathogens that remain on that surface after it has been cleaned.
And the standard for sanitizing is incredibly high. The FDA requires a 5-log reduction. I actually had to look this up because it sounds like math homework.
Yeah, it does.
A 5-log reduction means destroying 99.999% of the target microorganisms on a surface.
Exactly. It's essentially total eradication. But the absolute golden rule of kitchen chemistry, the thing that fails health inspections constantly, is this. You cannot sanitize a dirty surface.
Wait, really? Because I guarantee people do this at home all the time.
Oh, all the time.
You know, you have a greasy stove top after frying bacon, or a cutting board with raw chicken juices on it, and you just grab a bottle of Clorox spray, mist it heavily over the mess, wipe it around with a paper towel, and think, okay, the bleach killed the bacteria, it's sanitized.
And they are completely wrong. The FDA actually refers to this as the false safety trap.
Okay, why?
If you spray a chemical sanitizer onto a surface that is covered in grease, proteins, or organic soil, the soil acts as a physical shield. The bacteria just hide under the microscopic layer of grease.
Oh.
Yeah. Furthermore, the organic matter actually interacts chemically with the sanitizer and neutralizes it. It destroys the chemical's efficacy before it ever reaches the pathogens.
Wow. Okay, so the grease essentially absorbs the chemical. It's almost like trying to put sunscreen on while you're wearing a winter jacket. You can spray all the SPF 50 you want, but the UV rays are still going to hit your face if your face is exposed, while the jacket just absorbs the chemical. You haven't protected the surface underneath. You have to take the jacket off first. Like, you have to remove the grease with soap and water before the chemical can actually touch the surface and do its job.
That is an excellent analogy. You wash with soap and water,
Yeah.
you rinse away the soap with clean water, and then, only when the surface is physically clean, do you apply the sanitizer.
So what exactly are these approved sanitizers? What is the FDA allowing commercial kitchens to use to guarantee that 99.999% kill rate?
The Food Code outlines 3 primary methods for sanitizing food contact surfaces. First is thermal sanitization using hot water, but it has to be extremely hot, specifically 171 degrees Fahrenheit for a minimum of 30 seconds of full immersion.
You can't just run that from a tap.
No, you see this mostly in high-temperature commercial dishwashers or massive 3-compartment sinks with internal heating elements. For chemical sanitizers, which are used in buckets to wipe down prep tables, meat slicers, and stationary equipment, the 2 most common are chlorine and quaternary ammonium, which is usually just called quat.
Chlorine is basically just bleach, right?
It is, but in a commercial setting, the concentration has to be incredibly precise. The FDA requires chlorine sanitizer to be maintained between 50 and 100 parts per million, or ppm.
That sounds like a really tight window.
It is. If it drops below 50 ppm, it isn't strong enough to achieve the 5-log reduction. The bacteria survives. But if an overzealous cook pours too much bleach in and it goes above 100 ppm, it becomes a toxic chemical hazard that can leave dangerous residue on the food prep tables.
Oh, wow. So it's a Goldilocks situation.
Exactly. Quat sanitizers typically are required to be right around 200 ppm, which is a bit more stable but still needs monitoring.
And how on earth does a manager verify that during a shift? I mean, they can't just eyeball a red bucket of water and know if it's at 200 parts per million.
They use specialized chemical test strips. They dip a strip into the bucket, it changes color based on the chemical reaction, and they match it to a highly specific color chart.
Like testing cool water.
Very much like that. They have to do this constantly throughout the day. The sanitizer solution degrades over time, especially as airborne particles or slight amounts of food debris from the towels get introduced into the bucket.
Which brings up the 4-hour rule again, but this time for cleaning.
Right. Any food contact surface that is in continuous use, say, a cutting board at a busy deli where they are making sandwiches nonstop, must be fully cleaned and sanitized at least every 4 hours. You halt production, scrub the board with soap, rinse it, sanitize it, and start fresh.
Why 4 hours again?
Because after 4 hours, the bacterial load on that board has reached a critical mass where ambient temperature allows them to multiply dangerously.
And when you see a cook wiping down a counter between those 4-hour deep cleans, there are strict rules for the towel they use, aren't there? I feel like I've walked into a coffee shop and seen a damp, milky rag just sitting on the counter next to the espresso machine.
That is an automatic core violation, and it is a massive pet peeve for health inspectors.
Really?
Oh, yeah. Wiping cloths can never be left sitting out on a counter or tucked into an apron string. A damp, warm towel with mick residue on it is the perfect breeding ground for bacteria. When not in active use, that towel must be stored fully submerged in a bucket of active, tested sanitizer solution.
And after you sanitize a piece of equipment, you can't just dry it off with a towel either, right?
Never. All equipment, pots, and dishes must air dry.
Really? Air dry only?
Yes. If you run a massive soup pot through a 171-degree sanitizing dishwasher, it comes out sterile. If you then dry it with a cloth towel that's been hanging in the kitchen, you just completely recontaminated the pot with whatever was on that towel. Air drying is the only legally approved method.
Wow, okay. So we are blasting surfaces with 200 parts per million of quat sanitizer. We are submerging towels. We are charting temperatures. It sounds foolproof. But if that chemical requires a perfectly smooth, clean surface to work, what happens when the stainless steel table itself starts to degrade? We've been talking about the food, the tools, and the chemicals. But what if the problem is the building itself?
Now you're entering the realm of macro-level food safety and the domain of the Food Safety Modernization Act, or FSMA.
Yeah, our sources discuss a major philosophical shift in how the FDA handles commercial food production, moving from a reactive stance to a preventive one with FSMA.
Historically, the FDA operated somewhat reactively. A bunch of people would end up in the hospital with salmonella, an outbreak would be identified by the CDC, and the FDA would go in after the fact to figure out what went wrong and force a recall.
Right.
FSMA changed that entirely. It forces massive production facilities and corporate kitchens to anticipate where hazards might occur and build engineered systems to prevent them before a single product ever leaves the loading dock.
And a big part of that is Rule 204, the traceability mandate. The sources mention that inspectors now expect facilities to trace a batch of food from the farm to the distribution center in hours, not weeks.
Imagine a scenario where a specific batch of romaine lettuce is linked to an E. coli outbreak. In the old days, it might take investigators weeks of digging through physical paper invoices to figure out which farm in California grew the lettuce, which trucking company transported it, and which facility chopped and bagged it.
And by then it's too late.
Exactly. By the time they found the source, the contaminated lettuce had already been eaten by consumers nationwide. Under FSMA Rule 204, utilizing digital traceability systems, a facility must be able to pull up the entire supply chain history of that specific batch in a matter of hours. They can pinpoint the exact field it was grown in and issue a highly targeted, localized recall instantly.
That is incredible. And the technology they are using to enforce this is practically science fiction. The sources outline how regulators use something called Whole-Genome Sequencing, or WGS.
WGS is an absolute game changer for regulators. It's basically a highly specific DNA fingerprint for a single strain of bacteria.
How does that actually play out in the real world? Say an inspector walks into a processing plant.
Okay, let's say an FDA inspector swabs a trench drain in a food processing facility in Ohio, and the lab finds a strain of listeria. They sequence its genome, they map its exact DNA structure, and they upload that genetic barcode to a national CDC database.
Okay.
The plant cleans the drain, life goes on. 2 years later, there is a mysterious outbreak of listeria illnesses in California and New York. The hospital sequenced the bacteria from the sick patients. If the genome from the patients is a 100% match to the swab taken from that drain in Ohio 2 years prior, the regulators have their culprit.
That is insane.
You can link a nationwide multi-state outbreak directly back to a specific puddle of water on a specific processing floor from years ago. There is nowhere to hide.
That is wild. They can track the DNA of the bacteria back to a specific puddle, and that perfectly explains why modern facilities are obsessed with what the manuals call zero-harborage design.
Yes.
Because if regulators are tracking bacteria that closely, you literally cannot give the pathogens anywhere to hide in the architecture of the building.
If we connect this to the bigger picture of facility design, you realize that contamination rarely just falls out of the air. Bacteria needs a home. It forms in physical harborages areas with trapped moisture, food dust, hollow frame tubing on equipment legs, unsealed joints, and warmth, where bacterial biofilms can flourish and resist cleaning.
Give me an example of how they engineer that out of a building. I saw something in the equipment specs about avoiding dissimilar metals. What does the type of metal have to do with bacteria?
It has everything to do with it. When certain different metals touch each other in a wet environment, say in an aluminum bracket bolted to a carbon steel frame in a washdown area, they cause something called galvanic corrosion.
Okay, like a battery.
Sort of. An electrical reaction occurs that causes the metal to slowly degrade and create microscopic pits on the surface. To the naked eye, the metal looks perfectly smooth. But under an electron microscope, it's a rugged landscape of craters.
Oh, I see.
Bacteria like Salmonella will settle deep into those microscopic craters. Once they wipe the surface with a sanitizer cloth, the chemical just glides right over the top of the craters. The bacteria is protected in its little bunker. So facilities must use specific, seamless, non-corrosive metals, like 316 grade stainless steel, with fully welded and polished joints to prevent pitting.
It's like trying to sweep dust out of a pothole. You have to pave the road smooth before the broom actually works.
That's a great way to put it.
What about the air in the room? The sources mention HVAC systems as a food safety tool.
Airflow is heavily engineered. High relative humidity accelerates bacterial growth. So modern facilities use positive pressure HVAC systems with heavy filtration to control the environment.
Positive pressure, meaning the air pressure inside the sterile prep room is literally higher than the air pressure in the hallway or the loading dock.
Exactly. Think about when you open the door to a clean packaging zone. Because the mechanical air pressure is higher inside, the air forcefully rushes out through the doorway, blowing away from the clean zone into the dirtier hallway.
Wow.
It creates an invisible barrier that prevents dust, airborne mold spores, and pathogens from drifting into the sterile environment.
It's an invisible force field made of air. That is brilliant. And finally, water. You mentioned the DNA swab from a drain earlier?
Drain dynamics are critical. The entire floor of a commercial facility must be mathematically sloped towards seamless stainless steel trench drains. Water cannot be allowed to pool anywhere because standing water is a harborage. and the staff have to be incredibly careful about how they clean those floors.
Because you don't want to splash the dirty drain water around.
It's worse than splashing. You never point a high-pressure hose directly into a floor drain.
Why not?
If you do, the high-pressure water hits the contaminated water in the drain and aerosolizes the bacteria. It creates a microscopic, invisible mist of pathogens that floats up into the air and eventually settles all over the clean prep tables you just spent 4 hours sanitizing.
Oh man, it's a completely interconnected ecosystem. If a dishwasher messes up the angle of a hose on the floor, they instantly ruin the chemical sanitization on the table 10 feet away.
Exactly.
So what does this all mean? We started this deep dive looking at a simple blue letter grade in a restaurant window. And what we've uncovered is that dining out safely isn't just about a manager with a clipboard checking off boxes. It is the result of a massive, coordinated scientific effort.
It really is.
It has the rigid vertical hierarchy of the walk-in cooler, the distinct color of a cutting board, the precise parts per million of the bleach bucket, the 6-inch gap under the storage shelf, the genetic DNA sequencing of a drain swab, and the positive air pressure in the ceiling. All of these systems have to run flawlessly in parallel every single day to ensure that the meal on your plate doesn't make you sick.
It is a remarkable achievement of modern public health and engineering. But zooming out, it does leave us with a rather provocative thought to ponder.
What's that?
Despite all of this incredible science, the seamless stainless steel, the thermal sanitizing dishwashers, the genetic traceability, the weakest link in the entire chain remains the human element.
The stress line cooks skipping the 20-second hand wash on a Friday night because they're behind on orders. The false security of a pair of latex gloves.
Exactly. The human factor is the one variable you can never perfectly engineer or control, which raises a really important question for the future of the industry. With the rapid rise of automation and robotics in commercial food service, will the only way to achieve a permanent, guaranteed perfect score in a zero-harborage facility be to eventually remove humans from the commercial kitchen entirely?
Wow. A completely sterile robotic kitchen. That puts a whole new spin on the idea of a flawless health inspection.
Doesn't it?
Yeah. The next time you see that bright blue A in the window of your favorite spot, just take a second to appreciate the sheer volume of science, discipline, and maybe a little bit of luck with the human element that went into earning it. Thanks for joining us on this deep dive into the hidden world of commercial food safety.